Hey, AstroHub fam! Ever wonder what happens when you cram 10 million stars into one cosmic neighborhood? Well, turns out you get some pretty wild stuff, including hidden giants. Today, we're diving into the mystery of Omega Centauri and the incredible hunt for something we can't even see. So, how do you find something that doesn't shine, doesn't emit any light, and is just quietly lurking in the dark? That's the cosmic hide and seek we're playing today on AstroHub. So, imagine a huge family of stars, right? Not just a few hundred, but millions of them, all hanging out together, held in place by their own gravity. That's what we call a star cluster. And among all the star clusters in our Milky Way galaxy, Omega Centauri is like the absolute superstar. It's massive, super bright, and get this, if you're in the southern hemisphere on a clear night, you can actually see it with your own eyes. How cool is that? This cluster is seriously ancient, like over 12 billion years old. To give you some perspective, our sun is only about 4.6 billion years old. Because Omega Centauri is so old, a lot of its really massive stars have already lived their full lives and, well, gone out with a bang. When those super heavy stars die, they explode in something called a supernova, a truly spectacular event. And sometimes what's left behind is something super dense and completely invisible, a black hole. So, it made total sense for scientists to think, hey, Omega Centauri should be absolutely packed with these things. We're talking about a cluster that's about 17,900 light-years away, crammed with a mind-boggling 10 million stars. All that adds up to a total mass equal to about 4 million of our own suns. Seriously, talk about a cosmic heavyweight. So if Omega Centauri is this super old, supermassive cluster with all those really heavy stars dying out, you'd think there should be tons of black holes hanging around, right? I mean, logic totally points to yes. Some scientists even predicted there could be as many as 10,000 stellar mass black holes there. Now, stellar mass just means a black hole that formed from a single giant star. They thought 10,000 of these guys would be lurking right in the cluster's center. But here's the tricky part, and it's a big one. Black holes are incredibly difficult to find. They don't give off any light at all, so they're literally invisible to us. The only way we usually see them is when they're actually doing something, like actively munching on gas or even another star. When they snack like that, they tend to burp out energy in the form of X-rays and radio waves. It's kind of like a cosmic burglar alarm going off, letting us know they're there. But the big problem for Omega Centauri is that it's super old and pretty desolate. What I mean by that is, most of the fresh gas and material that black holes love to snack on is long gone from the cluster. So even if there are black holes, they're probably just sitting there quietly in the dark, not doing anything to give themselves away. So you might be thinking, even if these black holes form, couldn't they just get kicked out of the cluster? And that's a really good question. When a supermassive star explodes to become a black hole, it's not always a perfectly even symmetrical event. Think of it like a wonky rocket launch. Sometimes that explosion can give the newly formed black hole a little push, a kick, sending it zooming off into space. You'd expect some of them to just fly right out of the cluster, right? But here's the thing. Omega Centauri isn't your average star cluster. Its gravity, that invisible pull that holds everything together, is incredibly strong. Like, almost twice as powerful as most other clusters we know. We measure this strength using something called escape velocity. That's basically how fast you'd need to be going to totally break free from a celestial body's gravitational grip. For Omega Centauri, that escape velocity is a whopping 62 kilometers per second. That's super, super fast. So, even if a black hole gets a little kick from its fiery birth, it's usually just not enough to escape Omega Centauri's intense pull. It's kind of like trying to jump out of a really, really deep pit. You'd need an absolutely massive jump to get out. Because of this powerful gravity, all the scientific models and simulations tell us that these black holes should definitely still be there, trapped inside the cluster, even if they're just quietly lurking in the dark and not putting on any kind of light show for us to easily spot. Okay, so we know these black holes are probably there, trapped in Omega Centauri, but they're not exactly putting on a show for us, right? No X-rays, no radio waves. So, astronomers had to get super creative. Instead of trying to see the black hole itself, which is impossible. They decided to look for its influence on something else. Think about it like this. Imagine you're walking your dog and your dog decides to hide behind a bush. You can't see the dog directly, right? But you can definitely see the leash moving and tugging. That's kind of what astronomers did. They started looking for stars that were being pulled around by some invisible force. They zeroed in on one particular star, just a regular-looking star, hanging out near the very center of Omega Centauri. It was about 1 light-year away from the exact middle, pretty close. Nothing super special about this star on its own, just a normal, everyday star. But after watching it for a seriously long time, over 2 whole decades, they noticed something really peculiar. Its path wasn't straight. Nope, it was doing this subtle, gentle curve. It was clearly orbiting something that they couldn't see. It's exactly like how our planets orbit the sun. We can't actually see gravity, but we definitely see its effects, right? We see Earth going around the sun year after year, and that tells us something huge is pulling on it. Now, to catch these tiny, subtle movements, astronomers needed some seriously powerful tools. They brought in the big guns, the Hubble Space Telescope, and, more recently, the James Webb Space Telescope. Imagine trying to see a tiny ant crawling on a football field from miles away. That's the kind of precision we're talking about. They actually collected data for an incredible 23 years. Think of it like making a super long time-lapse video, taking hundreds of pictures over 2 decades, and then stitching them all together. That allowed them to map out the star's path with incredible accuracy. What they found was that this star was orbiting an invisible companion, and it takes about 94 years for it to complete one full loop. We call that its period. Now they only watched it for 23 years, which isn't even a quarter of that full orbit, but they got super lucky. Around 2012, the star was at its periastron. That's just the fancy word for the point in its orbit where it's closest to the invisible object and, because of gravity, it's moving the fastest. This gave them a crucial peek at the most dynamic part of its journey, which was enough data to really nail down the companion's mass. By using something called Kepler's laws of planetary motion, these are just rules that explain how things orbit each other, like how Earth goes around the sun. They calculated that this invisible object was about 4.46 times the mass of our sun. And if something is that heavy but doesn't emit any light at all, well, there's really only one thing it can be, right? A black hole. So, this new black hole got a pretty cool name, Omega Centauri BH2. And if you're thinking, wait, why BH2 and not BH1 if it's the first one? That's a super good question. It turns out, earlier in 2024, scientists actually found a candidate for an intermediate mass black hole in Omega Centauri. That's a much bigger type, thousands of times the sun's mass. But BH2 is a stellar mass black hole, meaning it formed from just one single star, and it's the very first confirmed one of its kind in Omega Centauri. So it's a first for this specific type. What's really interesting is that BH2 is pretty light for a stellar mass black hole, especially coming from such an old cluster with low metallicity. Now, metallicity is just a fancy way of saying how many elements heavier than hydrogen and helium a star has. Old stars, like the ones in Omega Centauri, usually have low metallicity. And we used to think black holes from these stars would be much heavier, maybe 20 to 40 times the mass of our sun. But BH2 is only about 4 to 5 solar masses. This tells us something new and exciting. Even small stellar mass black holes can form in these super ancient environments. That means the universe might have a much wider variety of black hole sizes than we ever imagined. It really opens up new possibilities for how these cosmic behemoths form and evolve. The Webb telescope is actually going to keep watching this star in 2027 and 2028, which will give us even more precise data about its orbit and the black hole's mass. It's like unraveling a cosmic puzzle piece by piece, finding darkness hidden among the brightest lights. That's what astronomy is all about, right? The universe truly is a beautiful dance where darkness and light reveal each other's secrets.